I don't want to grow up, I'm a curious kid. The world has 100 questions I can...
Good evening and welcome to Unveiling the Dark Universe through the Dark Energy Survey. I'm Tucker Hyatt, founding director of Wonderfest, the Bay Area beacon of science, and I am honored to represent Inka Ross, who is here this evening, fresh from Hawaii. She's the illustrious founder of the Mt Tamalpais Astronomy Program. Our speaker this evening is Dr. Alexandra Amon, fellow of the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University. Alex, as I believe she'll let us address her, grew up in the tiny Caribbean nation of Trinidad and Tobago, just off the coast of Venezuela. She secured an island scholarship to attend the University of Edinburgh in Scotland, where she earned an undergraduate degree in physics and then a PhD in physics at the Royal Observatory, winning the Royal Astronomical Society's Thesis Prize. And her thesis did concern tonight's topic, dark energy. Lucky for us, Dr. Amon loves science outreach. She wants to make all the STEM fields, science, technology, engineering, and math, all those fields accessible and welcoming to everyone. I feel welcomed already, but it is our turn to make her feel welcome. Please, as they say, give it up for Stanford astrophysicist, Dr. Alex Amon. There you go. I heard a clap.
Thank you so much for having me. I hope you can hear me clearly, and I'll go ahead and take it away. So I'm super excited that this evening you can take an hour out of your day for something a little bit different. So even though we don't get to do this at the top of Mount Tam, I hope that the vastness of the universe that I'll tell you about makes up for that. So thinking about the universe is pretty special. Leaving aside the pretty pictures, the breathtaking landscapes, astrophysics forces us to think about grand ideas and to remove ourselves from the mundane day-to-day stuck on planet Earth, especially in the difficult time of a pandemic, and think a little bit bigger, or think a lot bigger. The universe brings us wonder, and looking up at the night sky has marveled ancient civilizations all the way to us here tonight. So we're really just continuing a long-standing tradition. Now, I do my research as part of the Dark Energy Survey, and here's the view of the telescope we use, nestled on a mountaintop in the deserts of Chile. And with the images that this telescope captures, our team of experts tries to answer big questions. So what is our universe made of? And how did it evolve to the way that we observe it today? Now, we humans are pretty terrible at imagining and understanding things that we have never experienced personally. So with that, it's not hard to conceive that we have flat earthers or people who can't accept climate change as a worrying fact. Astrophysicists, however, study the reaches of space and time, far beyond human experience. That by no means that we're without our preconceived biases, just that we're exceptionally lucky to be able to practice thinking outside the box. And so that's what I hope that we get to do tonight. So I'm going to start by telling you about some of my favorite times, or 6 favorite times, that the universe made us think outside the box and scratch our heads. Of course, I have a pretty biased opinion, but astronomy or cosmology, like no other field, has a history of turning our views totally upside down, so defying expectations and altering the way that we view our existence and our place in the universe. Then I'll tell you about where the field, cosmology, stands now, what we think we know. And finally, I'll tell you about the Dark Energy Survey, what we do, how we do it, and what we've learned so far. So to kick us off, our first head-scratching moment starts way back. So in the 1500s, Copernicus debunked humans' egocentric thinking that the Earth was at the center of everything that we knew. And the stars in the night sky revolved around us. And this was a very controversial and brave claim at the time, when astronomy and religion were closely tied. Now, thanks to him, initially, we now know that the sun sits at the center of our solar system, and the Earth is the third planet outward of 8, making a journey round and round. We now know that even our sun is a pretty unremarkable star, not very different to any other that we see in the night sky every day. Now, another revelation came, number 2, from someone who we've probably all heard of, Albert Einstein. He rewrote our understanding of gravity, the very law that governs everything that we know. So at the time, scientists were content with the fact that an apple, when let go, would hit the floor, or that if I threw a ball, I could predict exactly the arc that it would traverse when hurled through the air, and exactly what position and speed that it would land in on the other side of the room, motion governed by gravity. Isaac Newton's theory of gravity, the universal law of gravitation, has stood up to all of our observations here on Earth. But when astronomers started looking further away at larger scales and more extreme environments than here on Earth, there were cracks in this theory. So Newton's law couldn't quite explain, for example, the orbit of Mercury. So Einstein proposed an alternative theory for gravity, general relativity. Now, modifying the laws of gravity, that definitely needed evidence. So his theory proposed that any object that has a mass, whether it's a planet or an entire galaxy cluster, distorts the very fabric of our universe, space-time, as you can see depicted here. Now, as a result, light from faraway objects gets bent as it travels across space-time. Its path gets bent because the space-time is also bent. So it gets the path gets distorted by just the presence of these massive objects. He claimed that we should be able to see stars that are in fact behind the sun because their light would be bent due to the mass of the sun. And this would be the ultimate test of his theory. Of course, when the sun is up, we can't see any stars unless there's an eclipse. So in 1919, during a solar eclipse, teams set out to test this theory and found that he was right. His theory of gravity still stands today. And here were the New York Times headlines at the time. So while general relativity is now the bread and butter of your astrophysics degree, back in 1919, it was a blow to the way that we understood our universe. Lights all askew in the heavens, men of science more or less agog over the results. Now, the third thing I want to tell you about is some years on, Edwin Hubble was the face of the next shakeup in humans' understanding. So he was equipped with the Hooker telescope and its 100-inch mirror on top of Mount Wilson, California. And Hubble used the telescope's state-of-the-art light-gathering power to take a series of photographs of the Great Nebula in Andromeda. Now, for the first time, the images revealed faint stars in the nebula, shown in the image on the left-hand side. And Hubble calculated that the stars were at least 10 times further away than the furthest stars in the Milky Way. Aha! The Andromeda Nebula was really the Andromeda Galaxy. And this discovery implied that the other, even fainter spirals in the sky were probably also galaxies, even further away, and they were dubbed island universes. The belief that our Milky Way was all that there was went totally out the window. And to boast the advancements in technology, here's the state-of-the-art view of the Andromeda Galaxy, or M31, our nearest neighbor to the Milky Way. Now, the fourth item, early in the 1970s, there was yet another blow to the field. Vera Rubin, my personal favorite, set out to study the motions of stars in spiral galaxies. Now, the faster that stars are swirling around, the more gravity that you need to keep them glued into that galaxy structure. So what did she hypothesize that she would see? She thought that she would see that the stars at the edge of the galaxy would be rotating slower than the stars near the center. So if the Earth was further away from the sun, it would feel less force and it would be traveling around more slowly. But instead, she found something quite strange. The outer stars were traveling just as fast as the inner stars. What's more, she observed that they were traveling much more quickly than she would have expected overall. If we could count up all the stars in the galaxy, deduce the mass of the galaxy based on all these stars, and predict the resulting gravity, it seemed that the gravity couldn't be strong enough to be able to prevent all the stars from flying apart. So this had to mean one thing, that there was some invisible mass in the galaxy gluing everything together, its gravity gluing everything together. And we call it dark matter. And I love this photo, not only because did Vera Rubin redefine our understanding of the universe, but she redefined the idea of what a scientist looked like. Now, we now know that dark matter comprises more than 3/4 of the mass in almost all galaxies. It forms a much bigger, stable halo in which the light and the visible galaxy live. So thanks to gravity, dark matter acts as the glue that holds all the stars together, the building blocks of our universe. Another decade or two later, the second to last one, in 1995, humans' minds were boggled again with the exquisite Hubble Deep Field. The people must have thought that the director of Hubble Space Telescope was mad. Space Telescope was launched, and the director wanted to use his very special and coveted director's time on the best tool that we had in the field to look at absolutely nothing. So he insisted that the Hubble Space Telescope would spend 100 hours over 10 days pointing at a tiny patch of sky about 1/30th as wide as the moon near the Big Dipper's handle that was dark. We didn't know that anything was there. Now the Space Telescope's images changed the field again. After looking for long enough and collecting enough light into this beautiful bucket, the Hubble Space Telescope, it found more than 3,000 galaxies in that tiny smidgen of sky. The image is absolutely teeming with spiral, elliptical, irregular galaxies, proving once again that it is impossible to comprehend the magnitude of the universe without some head scratching and maybe some quiet comprehension of quite how majestic it is. So starting with these observations, we now think that the universe contains about 100 billion galaxies, and our Milky Way is just one of them. Finally, as recently as 1998, astronomers studied supernova, the cataclysmic end of a star's life, to determine how far away their host galaxies were. You see, supernova always happen at the same time in a star's life, when they are at a specific luminosity, like streetlights along a dark path. We know what they should look like, and so we use that fact to calibrate how far away the streetlight is, or how far away the host galaxy is. So we call them standard rulers of our universe. They help us understand distances. Now, two teams found in 1998, what they found still boggles us today. The universe was expanding, and that universe expansion, that expansion was getting faster and faster every day, an accelerated expansion. And we attribute this phenomenon to dark energy, a mysterious component that makes up most of all there is in our universe, not to be confused with dark matter. So where does that leave our understanding of the universe now? We now know that everything that we're familiar with, the stars, the planets, gases, they make up only 5% of everything there is in the universe. About 1/4 of the stuff is dark matter, and more than 2/3 of it is dark energy. So you see, time and time again, the universe has surprised us. None of these ideas were expected or even accepted easily, and they often came with wild resistance. But slowly, through the power of science and logic and reason, they were proven to be true. I've hopefully convinced you that we must keep an open mind when we're thinking about the universe, and more importantly, that we have to let the data that we use, the data that we take and the data that we find, we have to let that do the talking. So trust what the science and the peer-reviewed research tells us. And with that backdrop, now I can tell you where our model for the universe stands today. So we cosmologists try to understand the story of the universe, and there are pieces of this grand puzzle that we think we understand pretty well. So we know that 13.8 billion years ago, the universe was this hot, dense soup of particles with very tiny density fluctuations governed by quantum physics, so random density fluctuations. We know that the universe underwent a period of rapid expansion called inflation, and this left an imprint of those tiny fluctuations at the time. Now, this bit is important. We call this the first light of the universe, the cosmic microwave background. And that the cosmic microwave background, when we measure it, gives us a map of the fluctuations in temperature and density from the early universe. So it is an imprint of the surface of last scattering, the first light that was available in the universe. And you can see a snippet of the cosmic microwave background measurements, the map made based on measurements in the bottom left-hand side there. And we know that as the expansion of the universe marched on, those tiny fluctuations cooled and expanded even further, such that eventually they would seed the large-scale structure in the universe that we observe today. And that's now shown in a snippet in the bottom left. So the parts that were the most dense to start with formed the first clumps of particles, eventually the first stars and the galaxies, and today the biggest galaxy clusters. The parts that were the least dense would be the voids that we see in our universe now, with less matter than everywhere else. So the random pattern in the cosmic microwave background is responsible for the pattern of large-scale structure that we observe in the cosmic web today. Now we know that right now the universe's expansion is getting faster and faster every day. And we attribute this observed phenomenon to a universe that is dominated by dark energy. We know that our universe is a cosmic web with dark matter clusters and filaments forming the bones of our universe, upon which galaxies live. So in the simulation shown here, the complex web structures of dark matter are shown in black, guiding the location of the relatively rare clumps of baryonic or normal matter, such as stars and galaxies, shown in orange. And so this simulation snapshot that I'm showing here is a simulation that was actually developed at Stanford and SLAC, called the dark sky simulations. And so the universe is kind of like Christmas lights, where the visible matter lives, where the light lives. It's like Christmas lights wrapped around a dark matter scaffolding. Now, dark matter does the job of gluing galaxies together, and that's crucial to the formation of structure in our universe. And dark energy is this evil sibling that undoes all that good work, pulling structures further and further apart and driving the accelerated expansion of the universe. Dark matter and dark energy may seem like hocus pocus, or even that they are something that we here on Earth don't really need to care about. But without them, our universe would not have evolved to the way that we observe it today. You see, our universe was concocted with the most precise recipe. Now, I don't know if any of you bake, but unlike how I do, for the universe, there is no imprecise dash of this or handful of that. There's definitely no recipe replacements. Without a certain amount of dark matter, there would not have been enough mass in the early stages of the universe to seed the structure of galaxies, which became comfortable hosts for planets like our own. Without a specific percentage of dark energy, there would have been too much structure. So without dark matter and dark energy and their cosmic battle against each other, it's likely that we simply would not exist. Now, this is the foundation of our dark universe, and it's very well described by our standard model of cosmology. So using a handful of parameters, this model can describe the evolution of our universe exceptionally well. We can make all kinds of measurements for our universe, whether it's exploding stars or mapping the velocities of galaxies, measuring the first light in the universe that began its journey 13.8 billion years ago. And it's really quite remarkable that these very different kinds of observations in our insignificant snippet in the grand story of the universe, we can make these observations and that we find that they mostly fit this consistent model. Mostly our standard model of cosmology works. But there's an elephant in the room, obviously. What is dark matter? Well, the short answer is that we don't really know. There are fascinating and intricate experiments all around the world with particle physicists on the hunt for a dark matter particle. And though we have pretty good ideas and educated guesses for what they're looking for, the fact remains that the particle has not yet been detected. Dark energy remains even more elusive. And so cosmologists tried to tackle this from a different angle, partly by nudging the particle physicists to find the particle, but mostly and more seriously by studying the galaxies in our universe. So we can tell you where the dark matter is. We can tell you that we know it behaves like normal matter with respect to gravity, but that it does not interact with normal matter or with light. In fact, a dark matter particle would fly right through you and probably has in this time. Now, we can tell you how much dark energy there is, on the other hand. And so despite the elephant, our model holds up pretty well to whatever cosmological measurements we throw at it. And our instruments and our techniques improve, allowing for more precise measurements. So we just keep throwing in hope of filling the cracks in our model or reworking the structure of the model to something that we understand better. But how do we go about learning about something that is invisible? The one answer to do that is weak gravitational lensing, and that's where I come in. So imagine a far away galaxy. As it journeys across the universe or towards the front of the screen, it gets bent because the clumps of matter distort the very fabric of space-time, and the light that is traveling along that path gets distorted with it. This is the basis of Einstein's theory of general relativity, which was tested with that solar eclipse, but on a much larger scale and with much tinier effects. So this effect, this lensing effect, means that every image that we take is slightly distorted with the imprint of the cosmos between us and that galaxy. Galaxies whose light travel past the same structures of the universe acquire coherence distortions and alignments. And if we can measure these distortions with extreme precision, we gain an understanding of the chunk of the universe that light passed through. So that light is twisted and bent, the path is twisted and bent along the way as it passed a cluster and another cluster and a void, all the way to our telescopes. And so the image has acquired that information. It has the signature of the cosmos. So the gravity of all the structure in the universe acts like a lens, much like our glasses, to background galaxies, and hence we call it gravitational lensing. Now the effect on our images is really small. That's why it's called weak gravitational lensing. So small that we wouldn't notice these effects with our eyes. We need many galaxies and we make a statistical observation. Overall, they have a pattern. Now we can use weak lensing to tell us where the dark matter is. It's like our eyes can only see the light and so only detect the light in the galaxies. But lensing lets us put on these special glasses that reveal where the invisible missing mass really is, or where the dark matter is. But what if we had really beautiful imaging data covering huge chunks of the night sky? So if we didn't just target a single cluster, like what's shown here, or two clusters, but if we mapped the large-scale structure over a volume of the universe, a significant area and depth of the universe. So take the diagram above. It's a box of a toy universe. The yellow galaxies tell us about the block of the universe that the light passes through to get to the image plane at the front. Now, lensing isn't just about pretty pictures. We can use weak lensing to test our standard model of cosmology. It tells us how much dark matter there is, and it tells us how clumpy that matter is. So it tells us about the amount of structure in the universe, what that web is like, how dense it is. And now, what if we could slice our data depending on how far away the galaxies were? So we could take this box, but we can cut it into 4 slices and do the measurements again. Then we could learn about how the structure is changing over time or over the volume, over the depth of that box. So we could use the light from faraway galaxies and the technique of weak gravitational lensing to pin down the parameters that describe dark matter and dark energy, how structure is evolving. Now, here's one more story that I'm working on, and one that I secretly hope in the end, turns out like the other ones that we talked about at the start of the talk. So with unexpected results that force us to look a little bit closer and to think a little bit harder. So to get into that story, let's go back to this picture. The gold standard of our field comes from measurements of the cosmic microwave background, or the CMB for short. Now, the Planck satellite was launched into space, and it allowed us to peer back to the very beginning of time, a mere 380,000 years after the Big Bang. And it delivered this extremely high resolution and state-of-the-art map of minuscule temperature fluctuations that are shown here on the left. So this is the Planck cosmic microwave background map. Now, compared to the predictions of our standard model, the measurements that Planck made are an exquisite fit. They leave very little room for something other than that model. Now, my research focuses on the late time universe. So it's probing the current era dominated by dark energy. So rather than the cosmic microwave background, which is shown back here, it's probing the time more like today. Now, when we compare our observations of the late time universe to the same model that is so well measured by the CMB, we set up this very beautiful end-to-end test. And it's asking, can we use the same picture that fits the seeds of our universe to describe these vast structures that formed 13.8 billion years later? It's like having a baby picture at extremely high resolution, and until now, with the limitations in technology, only a very blurry adult picture. And we're trying to see if the adult is the same person as the baby, or the same model, the same DNA. But we also want to understand what happened along the way in the person's life, or in our case, in the evolution of the cosmos. Now, it's a particularly exciting time for cosmology. So let me set the scene for you. Technology has rapidly grown, and with the most powerful telescopes in the world, there are several teams performing weak lensing measurements independently. So we use much larger data sets than ever before, and we are desperate to see if what we find is consistent with that model measured by the CMB, or perhaps if we find cracks in the grand picture. And we can ask if we would expect there to be cracks. Should we expect that the same model that fits the seeds also fits these vast structures? Because we are measuring a totally different universe. The cosmic microwave background is seeing the universe when it's just a soup of particles, or right after it's a soup of particles. But our measurements of the late time universe are seeing galaxy clusters and voids. So this plot that I'm going to show, it's the only plot I'm going to show. It shows a compilation of the existing results that we have for the amount and the clumpiness of structure in the universe. And that's going to be on the y-axis. And on the x-axis is the year that the measurement was made. So now I've added a gray bar, and that indicates the best fit model to the cosmic microwave background as measured by Planck to stunning precision. So that bar is very narrow, it has little error. Now I've added all these colored data points, and they're from all the previous weak lensing experiments. So there were 3 main ones now shown in, I'm only showing 2 of them actually, I should update this, it's showing green and pink. And so I can highlight these a little bit. The pink ones are from the dark energy survey, which I'll tell you a lot more about. And the green ones are from the kilo degree survey, which is primarily European. There's also the Hyper Supreme Cam survey, which is primarily Japanese. And so apart from these 3 ongoing experiments, there are many more smaller experiments that do weak gravitational lensing over the last decade or 2. And now there's something particularly curious here. And so if you're not into statistics, let's think about it. None of these measurements disagree with the gray bar to any real significance. So there's nothing that's way off the plot. But statistics tells us that our measurements should fluctuate around the model. You should have noise. So what we see is that instead of fluctuating around the model, instead of there being some data points down here, some up here, lensing is persistently low. These late time measurements predict a slightly discordant model compared to what the early universe dictates. What they're saying is that they see that the universe is a lot smoother than expected. There's a lot less structure than what the early universe says there should be. So we have three options for what's happening here. It's either that the cosmic microwave background measurements are not quite right. But this is the state of the art of the field, and I definitely would not want to be the person who's making that claim. Now, lensing measurements, it could be, are missing something, but there are so many lensing measurements. So how are they all missing something? Now, do we need, so the third option is we need some new physics to fill in the cracks of our model. Now, this could be an extension to Einstein's theory of gravity, or an alteration to our model, our standard cosmological model. Now, as lensing is a relatively new field, the signal is very tiny, and because it dares to threaten this gold standard CMB measurement, it's fair to say that our results are under scrutiny. So to understand what's happening with this plot and these low measurements, we need more data. And that takes us to the Dark Energy Survey. So I play a leading role in this survey, and we've just released the key analysis of one of the most powerful cosmological data sets until now. That means that after years of work, we've added a new measurement to that plot, and we've been super careful to get that measurement as right as we can. And I'm going to tell you a little bit about a taster of how we make that measurement. So going from late nights at the telescope to one of the most telling measurements of the late universe. So you take a handful of flights through Santiago and over the mountainous Coquimbo region to La Serena, and then a rickety ride through the desert, climbing 2,200 meters of Cerro Tololo, and you get to the observatory, and this is the view. So up there, it is dry, it is high, and it is smack bang in the middle of nowhere. And that makes it one of the best observing sites in the world. The mountaintops have very thin atmospheres with unobstructed views in all directions, and deserts have less water particles in the atmosphere to distort the last step of the light's journey across the universe to our telescope. And the remoteness ensures that there's minimal light pollution, a truly dark sky. Now, the Victor Blanco telescope, the one that the Dark Energy Survey has its camera fixed on, stands the tallest on the summit. And it is simply gigantic. So there you can see an excited me for scale. Its aperture and its primary mirror are 4 meters, and it sits on the 4th story of the dome. And telescopes run under the basic principle that if you put a bigger bucket in the rain, you will collect more water. So the bigger the aperture or the primary mirror, the bigger the collecting surface for light particles, the bigger the buckets, that have traveled across space and time. And these light particles end by being destroyed in the CCDs of the camera. Now, speaking of CCDs, or charged coupled devices, the camera installed on the Blanco that we use for the Dark Energy Survey is called the Dark Energy Camera, and it is also huge. So it has a 3.3 foot lens, and it consists of 74 super sensitive charge CCD chips on a whopping total of 570 megapixels. So the best iPhone on the market has 12, I think. Now, it allows us to image 3 square degrees at one time to exquisite resolution. And that's an area of the sky about 14 times the size of the full moon, captured in just one pointing. So DCAM is pretty high maintenance to make these measurements. 24/7, it has to be cooled by a steady stream of liquid nitrogen, ensuring that the CCDs stay at a healthy minus 100 degrees Celsius. Now, observing life is pretty special. There's an afternoon meeting up at the telescope to make the observing plan for the night. And then you head back down for a quick dinner at the lodge. And then you climb the mountain again to get ready for observations. And once you're set up and ready to go, there's this really nice tradition that observers on the mountain emerge to watch the sunset. So we all watch the sun sink below the horizon. And sunset is pretty spectacular, but humans aren't the only ones who've noticed. So the visachas of Cerro Tololo, something like kangaroo rabbits, they gather at dusk too. And I heard this rumor and I didn't believe it until I saw it with my eyes. So at sundown at the observatory, astronomers and visachas are both wide-eyed facing west, watching the sun dip below the mountain. Now, the noticeable quiet at the mountaintop is broken a few hours before sunset as the large dome of the Blanco creaks open. The telescopes look like guardians of the sky, perched on the summit. Giant robots awakening almost at once to peer into the cosmos. Throughout the night, they rotate slowly, doing their work, and we tiptoe around them with these tiny headlights in the dark, taking what we can to learn about our universe. So we take images of very distant galaxies. On one night of observations, a full night, we can take about 150 exposures. So if we point at each part of the sky for approximately 5 exposures in order to stack or sum the exposures for a deeper image, then we can take 30 different pointings in one night. And each of these pointings is 3 square degrees, so giving us a total of 90 square degrees just in one night. So compared to the moon, which spans 0.2 square degrees on the sky. And each square arc minutes that we measure, we can image about 6 good galaxies. So galaxies that we resolve well enough to do science with. And that means in one night that we can image at least 1 million galaxies in our universe in just one night. I couldn't believe that number when I worked it out at the telescope one day, and I did it a few times to make sure it was right. So here's what a stacked and processed exposure looks like. And remember, 14 full moons can fit in this area that you're seeing here. And that odd-shaped field of view that the camera has is very clear. So you can see all the different CCDs. And when you zoom into each of these, like I've done for this one here, each little blob there is not a star, as I keep reminding my mum, but a galaxy, an entire galaxy on its own. So not just this big one at the front, but all the ones in the back as well. Now here are some particularly big, beautiful DES galaxies. And you can see that they really do come in all shapes and sizes. So to do a weak lensing analysis and to learn about dark matter and dark energy, we need 3 pieces of information from our images. The locations of the galaxies on the sky, that one's easy. The shapes of the galaxies so that we can estimate how distorted or how lensed they are. And we need to also understand how far away that galaxy is. So position, shape, and distance. Now, measuring shapes doesn't sound that hard. That's what I thought at the start of my PhD. But the galaxies that we're dealing with aren't quite the picturesque spirals like the one on the top left, but more like the fuzzy blobs on the right. So you see the light particles from a galaxy travel all the way across the universe, getting gravitationally lensed by the large-scale structure, encoding the secrets of the universe within them, until they get to Earth. And the Earth's atmosphere then smears and blurs the images, and then that happens some more thanks to the telescope. The detectors pixelate the image, and then there's noise. And even that galaxy image shown on the top right is a particularly nice one for weak lensing. Now we turn to measuring the distances to these galaxies. We use the fact that the galaxies that are further away will have slightly different colors compared to ones that are nearby. So ideally, we'd take a spectra for each galaxy, a spectrum for each galaxy. So we'd break the light into constituents and get the full spectrum as a function of wavelength. But that's a very expensive measurement to make. And we want images of lots of galaxies to do weak lensing. So instead, we observe each galaxy with different filters on our camera. And that's what's kind of depicted here, these colored bands as a function of wavelength. And by having measurements in different filters, it allows us to pick up different features in that galaxy and to measure colors. And from those colors, we can determine the distances to galaxies. Now, it's a little more complicated than that, because of blending, we call it. So as our telescopes are getting more powerful and we're able to take deeper images of our universe, resolving further away galaxies than previously possible, that means that fields are crowded and sometimes galaxy images get projected onto each other. And that actually happens quite a lot. So for this one shown here, there's what, 1, 2 big ones and maybe 3 small ones that we can see well and countless small ones that we can't see well. So how do you measure the shape of that mess? And even worse, what happens if they're all at different distances, different redshifts away from us? Now we do our best, and thanks to years of work by many people, we make a catalog of the positions, distances to, and shapes of galaxies that we have surveyed. Now, the field is rapidly advancing. Just a decade ago, weak lensing experiments used datasets that spanned areas a few times the size of the moon, and they boasted hundreds of thousands of galaxies. With the dark energy survey, it's a totally different game. Our data set spans 1/8 of the night sky. You can see that here, this beautiful map that was made of our data, and that's a dark matter map. We'll say a little bit more about that in a second. And it's underneath the band of the Milky Way. It's in the southern hemisphere. And it spans 1/8 of the night sky, cataloging more than 100 million galaxies. It really is a different game. And with such a powerful data set, not only do our data analysis techniques need to be good, but our model needs to be robust as well. Oh, and I thought I'd throw this in here. This is a jigsaw puzzle of the same map, which kept a lot of us busy during the pandemic. I can recommend those. Now, aside from our data, we need a theoretical model. So using our standard model of cosmology, we can make predictions for what our measurements should look like. So computer simulations are crucial here. And you see, any good school science experiment involves repetition. And I don't know how many of you remember this when you were at school, but when you're doing your experiments, perhaps you're growing tadpoles and you want to test which conditions are optimal. So you keep some in a container with pondweed and some in a container without pondweed, and you leave some of them in the pond. And you do this over and over with some factors being manipulated one at a time. But we have one universe. So computer simulations bring astronomy back to the laboratory setting. We can tweak our model and see what our universe looks like if we added a pinch more dark matter or took away dark energy. And so they really help us develop our model. Now, some parts of this model are quite tricky. We measure how similar galaxy shapes are or how aligned they are in our images due to weak lensing. But all that goes on the assumption that galaxies are really randomly shaped and oriented without the effect of weak lensing. So what if that's not true? What if galaxies are already aligned without any weak lensing? So galaxies that form in the same environments may already be aligned, and that would contaminate our signal. So here are 2 galaxies merging on the left, creating a natural alignment between them that has nothing to do with weak lensing. And on the right, there's this chance alignment of galaxies in a row, which we found in our images. It's really quite spectacular. So we need to account for this, the fact that galaxies might not be randomly oriented all the time. And there's this other sticking point. So it turns out galaxies are pretty complicated. They're not just these fuzzy blobs in our images, one of 100 million that we measure shapes of, that obey the rules of dark matter and dark energy. Sure, that's true on large scales, we can consider them like that, but on smaller scales, they have all these wonderful complex processes happening. So they might have black holes that spew particles to far-reaching extents in the universe. And these make modeling our measurements particularly tricky at small scales. So at scales like within this radius, whereas we think we can do it on larger scales. Now these challenges all add to the fun, whether it's the challenge of measuring shapes or distances or modeling. The Dark Energy Survey is this large team of scientists from all around the world, and it exemplifies that science can no longer portray this lone person scribbling over a parchment. These groundbreaking experiments that will change our understanding of the universe require a team of people working hard and hopefully a diverse set of people to bring the best ideas. And our international team has worked together to harness the data from the night sky and make intricate measurements of faraway galaxies. We fine-tuned our methods in the Dark Energy Survey as we worked through this enormous data set. And so that brings me back to this picture. Now, I want to emphasize that all that time, we did this analysis over 3 or 4 years, we had no idea what we would find or where this data point would lie on this map. So the most important point of what I say is what I think sometimes is really the value of science, is that it didn't matter which way I preferred this would turn out. So I think I did prefer, well, it doesn't even matter what I preferred. You can tell me that in the questions. But we do our entire analysis with obscured results. So we don't know whether our results will support our story of the universe or the standard model and be able to describe the same thing the CMB sees, or if we would find still more hints of new physics. So we made all our measurements and we tweak our model essentially with fake data for 3 years. And when we're sure we've done it right and we know how to do everything, then we rerun the analysis with one button, mostly one button, with the real Dark Energy Survey data. And so we're set up in a way that we cannot bias ourselves to the right answer or to the answer that we want, either consciously or unconsciously. And a few months ago, we released our findings, and this is what we found. So that pink data point now is about half the size of the one that came before from the Dark Energy Survey. And so our analysis gave us a clearer picture of the universe than ever before. And what we found is, in my opinion, intriguing and frustrating at the same time. So our measurements are well described by predictions from the standard model of cosmology. As before, they don't have any glaring disagreements with the gray line. They are as consistent as you would expect for one data point, but they add to this puzzling story that all of the lensing measurements are low. And remember, the backdrop of this story is that our universe is bizarre. It holds dark matter and dark energy at its core. Measurements of the early universe, the CMB, or the baby picture of our universe, they are an exquisite fit to this model, but they're probing a universe at an unrecognizable stage to the one that we're observing today with the Dark Energy Survey. These are two different measurements. And so we're really examining our standard model over cosmic time, and our analysis, while our analysis is best measuring how clumpy the matter in the universe is, so this value on the y-axis, it's intriguing that what we find is, again, slightly different to what the early universe dictates. And this difference isn't significant, as I said, but it does make us stop and scratch our heads as other lensing experiments like our own see this lowness. And so, again, we have to keep digging. I think this is where I meant frustrated. I hope that we would find something either bang on the early universe or really low. And so although our standard model survived another test more stringent than any other that came before, there's enough ambiguity to keep us intrigued. And so our standard model survives one more time, but we keep looking up. So where do we go from here? Well, there is still double the amount of data still to be analyzed from the Dark Energy Survey. So we just released the results from the first 3 years of observations, but we've taken 6 years. Now the survey is completed and we have 6 years of observations. So our work is just beginning. We're just at the beginning of learning what we can from the darkness, and that's extremely exciting. I mentioned these other surveys that are on the sky. So Dark Energy Survey is shown in this dark matter map. The kilodegree survey spans this blue area, and the Hyper Supreme Cam survey spans this orange area. And so one prospect that I'm particularly excited about is working together with the other teams to do a joint analysis. And then we'll have enough power to really see, is it very low and is there actually something wrong with our standard model, or are we just seeing some chance statistical fluctuation, and we're all seeing that? Now, the future is bright for our field, even looking ahead. It won't end with the Dark Energy Survey. Along with kids in Hyper Supreme Cam, HSC, we're really just the training ground for this bright future ahead. So this is a picture taken from the Blanco telescope, the Dark Energy Survey. And when you look just one mountaintop over, this is the Rubin Observatory under construction. So on the horizon to the Blanco telescope is the future of our field. And Rubin Observatory, Vera Rubin Observatory, will open a new eye to the universe. It will map the entire southern hemisphere every few nights. So for 10 years, it will keep stacking images until it makes essentially a movie of our sky, of the entire sky. And this will be a total game changer for our field. There is no doubt that the Vera Rubin Observatory will be game changing. In just a few years, the year one data sets from Rubin will contain more than 1 billion galaxies, so an order of magnitude larger than where we're at now. And it will go out to deeper, so further away galaxies than we've seen before for these types of measurements. And of course, with thanks to the team at SLAC and Stanford, the camera, which is shown here, is up and running, and it's ready to deliver high resolution images. And one of the first images that they took to test it out is this broccoli, which I think is hilarious. And I know that the guy who designed the telescope, the camera, who I work a lot with, had that broccoli for dinner that night. And there are 2 other telescopes that will be launched into space. I won't spend too much time on that. But I just want to say that one thing I'm sure of is that there will be many pieces of the puzzle to solve, even after the Dark Energy Survey and even after Rubin. It's hard to imagine what our field would look like in 10 years when we have data from Rubin. But I am sure that there will still be puzzle pieces to solve. So I encourage you to keep looking up and keep thinking big and keep asking questions. And with that, I can take any questions that you have now.
Wow, Alex, thank you. I know there are a lot of people that want to express their gratitude for that presentation, and I imagine to ask questions. I'll read 2 here in the chat, and I've got a few myself, but only if we run out of questions from our Mt Tam astronomy fans and the Wondernauts of Wonderfest. Dave asks, could you please explain how the shape of a galaxy seen in a telescope tells you the amount of structure in the universe?
Sure. So imagine, we can think about it just for one galaxy cluster. So one galaxy cluster is along our line of sight. So it's between us and the faraway galaxy that we're measuring with the Dark Energy Survey, for example. Now, the light from the Dark Energy Survey galaxy, the DES galaxy, has traveled across the universe, past this large galaxy cluster. And so its path has gotten bent along the way. That's the effect of gravitational lensing. Now that means because the path has been bent and wiggled along its journey, then the image of those background galaxies, the images of the galaxies behind the cluster, they are distorted slightly, not in a very strong way, but they're slightly distorted because their light has wiggled. It hasn't had a smooth journey all the way to planet Earth and our telescope. Now that's just the effect of one galaxy cluster, so one lens. But the same thing happens if you think of all the structure in the universe as a whole. So this cosmic web is now the lens, and it is between us and the faraway galaxy. And so if we understand that the shape of the background galaxy gets distorted as it travels through this cosmic web, it gets lensed due to the gravity of the cosmic web, then if we believe that the shape gets distorted, if we understand that, and if we can measure those distortions extremely well, then it tells us about the stuff that the light passed through. It tells us about everything that the light passed through. So it tells us about the cosmic web. And so because it tells us about the stuff that the light passed through, we can measure how much stuff it passed through or how clumpy that stuff was. So how much gravity was along the way, essentially.
Great.
That's a bit clearer.
Dave continues his question with this. What are the units for, quote, amount of structure in the universe, unquote? In other words, what does 0.8 mean?
Yeah, that's a good question. So I tried to keep it without units so that it's not, so that those numbers you can think of just compared to each other and not that they mean something on their own. In our standard model of cosmology, there are 5 or 6 parameters that describe the whole model. You just need a handful of parameters. One of those is omega matter, or the amount, the density parameter, how much matter, it represents how much matter there is in our universe. Another parameter is called sigma 8, and this is the clustering amplitude. So it tells you how much that structure forms a web instead of it being smooth. And that amount, that parameter that was on the y-axis is a combination of those two. It's some one times the other one to some power. So it's a combination of the omega matter and the sigma 8. And that's, we combine these two parameters because lensing can't tell you, it can't distinguish between those two. So if we think about the fact that the light from background galaxies gets bent along the way, we can't tell if the light has gotten bent by a lot of mass that was just very localized, or a little bit of mass, but everywhere. So it can't tell you the difference between the clumpiness and the amounts. So we parameterize this in this parameter. It's called S8. And the units of it are, it's designed to be unitless in the standard model.
Thank you, Alex. Let's take a question from somebody who will make himself visible and unmute himself. Carlos Secan, former Wonderfest speaker and frequent visitor to these great presentations. Dr. Secan, please ask your question.
Thank you, Tucker. First of all, this was a wonderful and very enlightening talk. I enjoyed it immensely. I have a pretty good conceptual understanding of dark matter, because we understand gravity, we understand the lensing effect and so on, and I assume it's huge computational effort. You can actually sort of calculate backwards from the distortions to some kind of structure in our universe. But I have a really hard time understanding dark energy. It seems like it's doing sort of the opposite of what gravity does. What is the mechanism or the model by which dark energy pushes things apart? And how can you compare in terms of how much there is in the universe between dark matter and dark energy, because they're so different things. I mean, if you measure it by their force, then they have different signs, so that doesn't work. So how can you compare the two? And what's really going on, when we say we have dark energy, and how can you even measure the amount of dark energy?
Yeah, these are brilliant questions. You're not the only one who's confused about dark energy. We all are, because we don't really know what it is. So there are a few different parts to this question. I'll start with the last one, which is how you tell with the opposite sign. They do indeed kind of do opposite things. So dark matter holds structures together, so particularly galaxies and galaxy clusters, it glues them together. Dark energy does undo that, but in a different way. So it doesn't it doesn't pull galaxies apart, rip galaxies apart, but it makes galaxies further apart. So the way that our universe is expanding, you can think of as if you're blowing up a balloon and you have 2 ants on the balloon, and each ant is a galaxy. Now you're blowing up the balloon and the ants don't get any bigger. So the ants aren't being ripped apart, thankfully. But the ants get further and further away from each other. So dark matter is keeping the ants together in that case, and not in pieces. And dark energy is making them grow apart. So they work in different ways.
So the dark energy is not really working on the masses. It seems to be working more on space and basically blowing up space.
It's pulling,
I see.
Yeah, it's creating more space between things. And so they do kind of have opposite signs, as you said, but in slightly different ways. So a really helpful way to understand it is with our simulations. We can make a simulation that has a little bit more dark matter and a little bit less dark energy, or switch off dark energy, and then we'd have way more web-like structure. We'd probably have too dense a universe for things like our planet to form. We would have collapsed. The gravity in our galaxy would have collapsed sooner. But if you had too much dark energy, then the web wouldn't have enough structure. So they kind of do different things. They do opposite signs in slightly different ways. And now computer simulations is a great way to test this. And on what dark energy is, I guess this is the money question. Our best bet of what it is. So I guess there are a few ways to describe it. One is it's the name for this observed acceleration, and we have no idea what it is. Einstein, it works into Einstein's general relativity equations as a cosmological constant. So we associate dark energy with the Einstein cosmological constant, but still, what is it? So we know the effect of it. We know how it fits in our equations, but what is it? And so we associate it with vacuum energy. So the energy that exists in a vacuum, in nothingness. And you can measure this in a lab with, like, I think it's called the Casimir Effect. So when you have a vacuum, you have these particles that can pop in and out of existence, and they annihilate each other with each other. You get a matter particle and an antimatter particle, and they will pop into existence and annihilate with each other and then disappear. And that creates energy and fuels a vacuum to create. So it's kind of a self-replenishing thing. It makes the vacuum grow. And so we think that's the mechanism for dark energy, but we don't really have proof of that. We know that vacuum energy exists in a lab, but we don't have proof that that's what dark energy is in our universe.
Yeah, but if it's so different from dark matter, how can you compare the two? How do you actually measure dark energy? I mean, and what are the units? I mean, is it grams or antigrams or what?
Yeah, sorry, I didn't explain this well. That's a good question. So we can measure dark matter because we can measure the structure, the amount of structure that is, as if we're weighing it on a scale. And when I said that we can take, so with the dark energy survey, we observe this 1/8 of the sky, and that's the area that we see on the sky, but it really is a volume because we can observe galaxies that are really nearby and then less nearby and less nearby when we think of that simulation box. And having the volume is key because the furthest away galaxies are looking further back in time at higher redshift. And so we take our volume that we observe in DES and we slice it up. We put it into 4 boxes, 4 separate boxes. So we took that simulation box that I showed and cut it into 4 chunks. And then you're setting up something quite nice because you can see the galaxies nearest to us and how much structure they have, make your measurement there. But you can also see the furthest away chunk and see how much structure it had that far back in time. And so then you're getting a sense of how the amount of structure and the amount of matter has changed with time. And that would be due to dark energy. So dark matter is constant in our model. It's always there. But dark energy is what's changing this acceleration. It's what's making the universe evolve.
So a strange hypothesis. If dark energy is doing sort of the opposite of what dark matter is doing, well, then if the dark matter is essentially increasing the clumpiness of the universe, maybe dark energy is a smoothing filter and smoothing out the clumpiness.
Yeah, it does kind of work like that as a smoothing field. And so that's why when we say we have deeper images, like when we do the next dark energy survey analysis, we don't get more area on the sky. We have twice as much data, but it was just looking at the same area. So we're really getting deeper images that allow us to look further back into the history of the universe. And that's going to be important for dark energy because then we can see more, we can better see how the structure is changing with time, you know, and test our model as a function of time.
Again, many thanks.
Yeah, thank you, Carlo. Here's a question from Rewa Bush. Thanks for sharing about your awesome work. I'm an astrophysics undergrad, and I'm excited by this research. How can you differentiate a galaxy that is photographed from an angle, not exactly face on, versus a lensed galaxy?
Yeah, that's a brilliant question. So we assume, well, we don't assume, all of our galaxies will be lensed. Every image that we take is lensed because the light has traveled through something to get something in our universe. So whether we're taking a picture of a galaxy that's the nearest to us, Andromeda, that has traveled through the least stuff in our universe to get to us. It's the closest galaxy. And that would be different to a galaxy that's the furthest away galaxy that we know of. That galaxy has traveled all the way across the universe to get to us. And so that will have a lot more lensing. So all the images that we take of faraway objects like galaxies, they are lensed, but to different degrees, depending on how far away they are, how much stuff in the universe they had to pass through. And so all of our galaxies, that's why we need a sample of 100 million galaxies, because we need to do this analysis statistically. So all our images are lensed, but we can't see that by eye. So we can never, you can't do lensing with one galaxy because you don't know what the galaxy looked like without lensing, and we'll never know that. So by doing it statistically, we can just draw patterns in the data. We can say that, okay, the ones in this patch, they're all kind of aligned that way. And then over here, they're all kind of aligned that way. We don't do it like by eye like this, but statistical measurements picks up the patterns in the data. And so your question is spot on, that with one galaxy, it's impossible. You'll never know what the truth is. Whether that galaxy was really that shape or it's stretched a little bit because of lensing. And that's why getting more data and being able to do this statistically is the only way we can make these measurements.
Alex, thank you. We've got a two-part question here from Nellie. I'll ask the second part first because I think it's broader and more mind expanding here. Also, sorry, when you refer to the fabric of space-time, is there more? Can you be more specific than that? Is the fabric itself dark energy?
Yeah, these are good questions. So the idea of space-time is Einstein's doing, and it is conceptual. It's not a real thing. It's just the fact that it's the same way that we think about the floor in your apartment. That's the space. So we know how that works. There's one axis and there's a perpendicular axis. So that you can go in all different directions in space. But in the universe, we also need the axis for time. And so that's why it's called space-time. And that's because there is not enough, that's because the universe is evolving as a function of time. And it's the axis that we can't go back and forth in, right? We can't go backwards in time. But we can see objects that are further away in time. So objects that are further away are us looking back in time. And so we define everything in the universe in this space-time coordinate frame or grid, but it's not a real thing. It's the same way you draw longitude and latitude lines on a map. They're not lines that exist in the real world, but they orient us in this space.
Good.
And so dark energy isn't this grid because it's not a real thing. It's just a coordinate frame like longitude and latitude. But we do think that dark energy is in that theory of it being a vacuum energy, then it's everywhere smoothly.
All right, Nellie at first asks also, could you explain a little bit more about what the consistent discrepancies you found with lensing experiments, what they indicate that there may be something not taken into account?
Yeah, let me get that plot up again. Oh, well, I don't need the plot. It could be that, I guess that's the question. What could be missing? So if we had let's say we had just one measurement here, or pretend we didn't have tens of them on this plot, but our recent measurement from the dark energy survey, I talked about all the different challenges that we have in doing this analysis. It's extremely difficult to measure shapes to that kind of precision. Estimating the distances to this galaxy is something that a lot of people worry about and we worry about in our analysis. It's one of the things that we spend the most time on, to understand and to estimate how far away each galaxy is in our data. And modeling how intrinsically aligned galaxies are, or modeling these small scale effects that galaxies are complicated. These are all challenges, and we can't do them perfectly. So we make for example, for measuring the distances to galaxies, we make an estimate for that distance, and we use simulations and use all these different methods to also provide an error bar on these measurements of distances. So we say, we think this galaxy is so far away, and we're unsure about that by this amount. But these are, I mean, in science, you have a data point and you have an error bar, and we're doing our best to get around these challenges, but they are still challenges. And so I guess we could be doing it wrong, I guess. And that blending thing is what's really hitting us most recently. When I talked about you have crowded images, and that's because it's new. We only now have these powerful telescopes that go deep enough that we're getting crowded images, like the one in my background here. We have these beautiful images. That means we have galaxies that are accidentally sitting on each other when it's projected to an image. And that's going to be really complicated going forward with with the last dark energy survey analysis, or with Rubin, because we have even better images, and they're all, every time you measure a galaxy, it's going to be a combination of many galaxies. And so that's something that I think could be an example of what we're doing wrong. But why that is looking implausible now is that these three teams that are working on it at the same time, the Dark Energy Survey, the PIDS, and HSC, we're doing it independently. They're very independent teams in different parts of the world, and we're all getting the same measurements. So we'd have to all be doing something wrong, or all be doing the same thing wrong coincidentally. And that's what's really bolstered this, whether this plot is concerning or not. It's the fact that many people are getting the same results. How can we all be missing something? That's what's intriguing to me. What is the thing that we could be missing?
Thank you, Alex, and thank you for the question, Nellie. Elisa Hamlet asks this: how can we see the cosmic microwaves from the Big Bang? Why isn't their origin too far from us to measure, that is beyond some kind of event horizon due to the speed of light?
That's a good question. So there are things that are not available for us to see because of that event horizon and the speed of light. The cosmic microwave background is the first thing that we can see. And that's because we can observe it not in optical images like the way we do our dark energy survey experiments. It's regular images that we're used to, like photographs. But when we're doing measurements of the cosmic microwave background, you take your images in the microwave or the radio. So they have the longest wavelength, and it's a totally different kind of measurements. You can see, well, the impact of the cosmic microwave background, not in modern day TVs, but when you get the on your TV, when you turn it on, when it doesn't have a signal, that noisiness, that's all relic microwave information from the Big Bang, which is quite exciting. It's like the leftover heat from the Big Bang, I guess, is the way you can think about it.
Yeah, in a sense, we're listening to the noise of the Big Bang.
Yeah.
Very cool.
Which was so accidental how they found it. They actually, when there were two teams. There was a theory team that hoped that they would see something like this, and there was an experimental team trying to measure something else, and in different parts of the US, I think. And the experimental team kept cleaning their telescope, their instruments, because they couldn't understand what was this noise they were getting. What is this? And they cleaned it over and over and worried that it was pigeon poo, and it was actually the detection of the cosmic microwave background. So if they could just speak to the other team sooner who was looking for this signal, they would have realized.
Oh, what a happy ending there. Instead of it being chicken poop, or sorry, pigeon poop. Yeah, it's a relic of the Big Bang. Great. Thanks, Alex. Let's see. Allison Bentley asks, I've heard dark energy called dark gravity, based on the idea that we don't really know exactly what it is. What do you think about that? Because are there alternate names for dark energy?
Yeah, I've never heard alternate names, but dark gravity would make sense in that we call it dark just because I think to represent that it doesn't interact with light like dark matter, but also to represent our ambiguity on what it is. And both dark energy and dark matter are really poorly named, in my opinion. Dark energy especially because it first of all, it sounds too similar to dark matter, and secondly, because we don't know what it is. It could be an energy in some way, and gravity would make sense. The name dark gravity would make sense to allude to the fact that it changes the way gravity works on large scales in our universe. So I've never heard that name. But certainly until we know what it is, surely the name will change at some point.
I'm just aware that we ought to take maybe one more question. Alex is so kind to stay with us here beyond the hour I promised her. By the way, she is speaking to us from the UK, where it is now 4, anyway, it's late. It's late at night, early in the morning for her. She began this talk at 3:30 her time, so we got to cut her some slack. I see that Greg J, who is brave enough to raise his hand and ask a question on camera. So let's make this the last one. And please forgive me for cutting off you other great questioners. Greg, take it away.
I remember hearing probably more than 10 years ago that with regard to vacuum energy as dark energy, the calculations of the magnitude of vacuum energy were 120 orders of magnitude bigger than the actual cosmological constant. Has there been any refinement of that gap or any inspired ideas about how to explain it?
No, that's exactly right. So the two elephants in the, I mean, this is why we keep doing these experiments, because our standard model is beautiful when you compare it to our observation. With the exception of this weird discrepancy that I just talked about, it mostly fits our observations, and in that way, it's a phenomenal model. But of course, it's built upon dark matter, which we haven't detected, and dark energy, which our best theory of it being a vacuum energy, it remains a theory because the calculation for that magnitude of the density of dark energy is totally wrong. And so I guess that's why it's intriguing, this beautiful model that is built upon things that we have no idea what they are. Then how will it change? I hope that's something we see in our life, in my lifetime, I guess.
Thank you.
Thanks for the question, Greg. Alex, is there a way for those of us who would like to pepper you with questions after this event is over? Can we follow you somehow? Can we even access your email account?
Sure, yes. So you can, I think my handle is here. So I'm Astro Alex Amon on Twitter and on Instagram. So you can follow me there and send me questions. And you can also email me. I guess if you search my name in Stanford, the email will come up. That's the easiest way.
Great.
It's my surname and then 2018 at stanford.edu.
Terrific. I end tonight by offering 3 big thank yous. First, to you, our Zoom audience. Thank you for being here and for asking such good questions. Second, to Mt Tam Astronomy and Wonderfest donors. We greatly appreciate you helping to keep science alive on the internet and in person eventually. Finally, and of course most important, we want to thank our speaker, Dr. Alexandra Amon. Perhaps we'll give her American Sign Language silent applause, maybe some clapping from the reactions so far. But Alex, you were just
So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists. Naming something doesn't mean that we get it. So I'll live each day with wonder. See the universe through a brand new set of
Right.